Hi there, welcome to this video. My name's John. I provide mathematics tuition for A-level maths, A-level further maths, 6-term examination papers and mathematics admissions tests. Very warm welcome to this video where we're going to take a look at a problem that I've selected from the 2015 mathematics admissions test, and it's question number 3 that we're going to be taking a look at in this particular video. So this is one of the more structured questions. For those of you familiar with the structure of the MAT, the first question is a series of multiple choice problems, which doesn't necessarily make them easy. But once you get onto question 2 and beyond, then you get more structured questions. So we're going to have a look at question 3. So this is a fairly straightforward problem for the most part. I've got a few notes here just to remind me what I need to go through. The last part is a little bit, it's easy, as with most problems, it's easy once you see exactly what you need to do. It's actually finding what you need to do in the first place. But don't be discouraged, this is part of the problem solving process. When it comes to solving a decent problem, what you'll find is that you spend most of your time trying to figure out which direction to go in. Once you get on the right path, the solution often writes itself. But a lot of the time people get discouraged by this because they think that they're spending too much time trying to figure out what to do rather than just doing what they need to do. That's problem solving. Okay, so this video, as with my many of my other videos where I go through MAT and step problems, it's not meant to be a model solution. Okay, so if you're looking for a model solution that just goes through and gets straight to the point, what the answers are and everything like that, look at the mark scheme or watch another video. Okay, what I'm looking to do here is to really, where appropriate and where I think it's going to be necessary and useful to do so, to point out the kind of things that I was maybe, where it's not obvious, what was I thinking about as I was solving this problem. For some parts it's obvious what you need to do and there's no difficulty at all. But for other parts it might be necessary for you to view things in a particular way. And I think this is something that a lot of people have difficulty with sometimes. The way that mathematics solutions to problems is often presented in textbooks and in the classroom, it's in a very polished form, and the fact that solution might have come about through a lot of hard work, a lot of trial and error, and viewing things in just the right way, come to an understanding of a problem that's right for solving that problem. This often goes unmentioned. So your textbooks and in the classroom, you can be sometimes, unfortunately, under the impression that you should just automatically see what you need to see. It doesn't work like that. So I'm wanting in this video and similar videos to really highlight the fact that problem solving is a messy process, and there's quite considerable work that you've got to put into solving a problem sometimes, and really it's finding that inspiration in the first place, finding the right direction to go in. Okay, so question number 3 then. So I will put a link in the description to this video so you can download the paper for yourself. I'll also put the question up on the screen at various points throughout the video so you can read it for yourself. There is quite a lot of information with this one. It's quite long in a certain sense. There's quite a few parts to it, but we'll get there. Okay, if there is anything that I don't explain particularly clearly, then just ask a question. Ask the question in the comments section. I'm not perfect. Sometimes I do miss things out. Sometimes I don't explain things perfectly. Just ask any questions that you need to ask. If you want me to go into more detail on something, I can always re-record the video further down the line if necessary. Okay, so let's give it a go then. So in this question, we shall investigate when functions are close approximations to each other. We define the modulus of x to be equal to x. Let me write this down. So the modulus of x is equal to x when x is greater. So this is just the bog standard definition of modulus function. If you don't know this definition, I'd recommend that you make sure that you know and understand this definition, because it is failure to understand this definition is something that causes so many A-level math students so many problems. Not knowing or not understanding this definition, precise definition of the modulus function, and thinking of the modulus function as just something that makes everything positive, which it does make things positive in a certain sense, but you need to understand what that sense is. Okay, so we got the definition of the modulus of x. With this notation, we say that a function f is an excellent approximation to a function if the modulus of f of x minus g of x is less than or equal to 1 over 320 whenever 0 is less than or equal to x is less than or equal to a half. So this is not something that you will see defined anywhere else. Okay, that's the whole point. You're given a new idea. You're having something defined that you've never had defined before. In this case, it's the notion of excellent approximation. So we're told that an excellent approximation is basically what this says. Okay, modulus of f of x. So what is it? F is an excellent approximation of a function function g if these conditions hold. Pay close attention to the fact that we've got 0 is less than or equal to x is less than or equal to a half. Why has the number 1 over 320 been chosen? Because it has. Okay, there's nothing special about it. This is not something that you will see defined anywhere else in mathematics other than on this particular MAT paper. And that's the whole point. That you're given something new that you've never seen before, can never have seen before, probably will never see before, to see whether you can handle being given new definitions. Okay, and then we're also told that f is a good approximation to a function g if the modulus of f of x minus g of x is less than or equal to 1 over 100. Again, for 0 is less than or equal to x is less than or equal to a half. Now you might ask, why do we have to have 0 is less than or equal to x is less than or equal to a half? The answer to that is because that's the definition. There is no reason other than that's how the author of this particular problem has decided to define this particular concept. So then we're told, for example, any function f is an excellent approximation to itself. If f is an excellent approximation to g, then f is certainly a good approximation to g, but the converse need not hold. Okay? So you can see that from the definitions, that if something is an excellent approximation, f is an excellent approximation of g, then it must also be a good approximation, but not vice versa. Okay, so question number 1 then. Let's get going. Question number 1. Or I. Give an example of two functions f and g such that f is a good approximation to g, but f is not an excellent approximation to g. So you're spoiled for choice here. Really, all that's being tested here is that you grasp the definitions. That's what you're being expected to show, that you have a sufficient grasp of these two definitions. So there is no need to make things any more complicated than they need to be. Choose simple functions and you can't go wrong. Okay, so what do I mean by simple functions? Well, we might choose something like f of x equals x and g of x equals x plus 1 over 200. Okay, because in that case, modulus of f of x minus g of x, and do write this by the way, actually show that your functions satisfy the definitions. Don't leave this to the imagination of your examiner. Make everything as clear as you can to your examiner. Even if you think it's obvious, that blatantly obvious what you're getting at, say it, put it actually on the page in black and white so your examiner can see exactly what you're thinking, because they can't see inside your head, and if it's not written on the page, basically it doesn't exist. So this is equal to the modulus of x minus 1 over 200, which is equal to the modulus of minus 1 over 200. Oh, not 1,200. Minus 200, which is equal to 1 over 200. Now, this is clearly less than 1 over 200 is less than 1 over 100. So f of x is a good approximation to g of x. And again, write it out. Just take the bit of time that it takes. Don't balk at it. Just get on with it. But also, 1 over 200 is greater than 1 over, what was it, 320? 320. So f of x is not an excellent approximation to g of x. We've also got that other condition, remember, that 0 is less than or equal to x is less than or equal to a half. And maybe I should put that in here. So f of x, modulus of f of x minus g of x is equal to this, is equal to 1 over 200, whenever 0 is less than or equal to x is less than or equal to half. Okay. Now, it actually holds for all x. But this is part of the definition. 0 is less than or equal to x is less than or equal to a half is part of the definition. So we need to make sure that we need to emphasize that that part of the definition is satisfied. Again, don't leave it to the imagination of your examiner. Just do it. Okay. So that's one possibility. I mean, there's an infinite number of possibilities that you could choose here. There's nothing that specifically prompted me towards that. You could choose f of x equals 0 and g of x equals 1 over 101. Okay, this will be perfectly fine. You choose what you want to do, right? But you're really just demonstrating that you've grasped the definitions. So no difficulties there. Part 2. Show that if f of x equals x and g of x equals x plus sine 4x squared over 400, then f is an excellent approximation to g. Okay, so let's start out then. So modulus of f of x minus g of x is equal to the modulus of, what was it, x minus sine 4x squared over 400, which equals 1 over 400, the modulus of sine 4x squared. Now, the modulus sine 4x squared, modulus of sine 4x squared is less than or equal to 1. Okay, so that means that 1 over 400 modulus of sine 4x squared is less than or equal to 1 over 400, which is less than or equal to, obviously it's less than, but we can write less than or equal to 1 over 320. So modulus of f, again, just point everything out to your examiner. I keep saying it, but it's so important. You might think that this is just so obvious that it's not even worth writing. It is worth writing, and do write it. f of x minus g of x is less than or equal to 1 over 320. For 0, less than or equal to x, less than or equal to a half, don't forget. So, by definition, f is an excellent approximation of g. Okay? So, that is how I would present my solution in this if I was sitting this particular exam, that is how I would be looking to present my solution. Okay, so again, no problems there. So then moving on, let me scroll down a little bit so I've got a bit more space. For the remainder of the question, we are going to try to find a good approximation to the exponential function. This function, which we shall call h, satisfies the following equation. So h of x equals 1 plus the integral from 0 to x of h of t dt. So h of x, this is effectively our exponential function, which if you think about it, the exponential function does satisfy this equation. But hang on a second, we've got some additional comments that we need to pay attention to. So whenever x is greater than or equal to 0, you may, and this is in boldface, you may not use any other properties of the exponential function during this question, and any attempts to do so will receive no marks. Okay, so what does that mean? It means the only property of the exponential we've just got this function called the exponential function. We know nothing about it effectively except this, what we've been told. Okay, that this exponential function h of x satisfies this particular equation. So even though you know full well what the exponential function is and you've got a good idea of a lot of its properties, do not be tempted to use any of those properties. Okay, at least not explicitly in your solution. Right? So I'm not saying that you can't have in the back of your mind some of the properties of exponential functions if you think they're going to be useful, because obviously nobody can see that. But don't put it down on the page, right? You've got to keep that stuff to yourself, or at least if you do put it down on the page, scribble it out so that it's clear it's not part of your solution. Right, so then we've also got let f of x. I'll write it on the screen here, but I will be putting the question up on the screen anyway. 1 plus x squared over 2 plus x cubed over 6. Some of you will probably recognise that this is these are the first 4 terms of the Taylor expansion of e to the power of x around 0. Not that you need to know that, by the way. If you're doing normal maths, probably you haven't come across Taylor expansions. Maybe if you're doing further maths, you might not have even come across them yet by the time you do the MAT. But you don't need to know. They're just an interesting little fact. Okay, so show that. So question number 3, or part 3. Show that if g of x is equal to 1 plus the integral from 0 to x of f of t dt, then f is an excellent approximation to g. Okay, so we need to show that f is an excellent approximation to g. So I may as well scroll down, give myself plenty of space for this. So I need to start out by calculating modulus of f of x minus g of x. Okay. So this is equal to the modulus of, so f of x is, what was it? Let me just remind myself. 1 plus x, right. 1 plus x squared over 2 plus x cubed over 6. And okay, so as a little aside, I need to do the integral from 0 to x of f of t dt. Okay, so this is equal to the integral from 0 to x of 1 plus t squared over 2 plus t cubed over 6. I mean, this is just easy, basic integration, right? This shouldn't present any difficulties. So it's t plus t squared over 2 plus t cubed over 6 plus t to the 4th over 24 between 0 and x, which is just equal to x plus x squared over 2 plus x cubed over 6 plus x to the power of 4 over 24. Okay, so subtracting g of x, I get minus x squared over 2 minus x cubed over 6 minus x to the power of 4 over 24 modulus. So there's a lot of cancelling here. Sorry. No, G was 1 plus, wasn't it? So actually, let me just... I need to squeeze an extra minus 1 in there. So minus 1 minus... Yeah, because g of x is 1 plus the integral from 0 to x of f of t dt. So then we get some cancelling. So 1 cancels with 1. X cancels with minus x. X squared over 2. X cubed over 6. So this modulus is just equal to the modulus of minus x to the power of 4 over 24. And for the maximum value, so the maximum value of this is going to be of x to the power of 4 over... Okay, so I can get rid of the minus sign, actually. So it's just going to be x to the power of 4 over 24. Since x is positive, x is greater than or equal to 0. In fact, we need that x to be between 0 and half. So this is equal to, is less than or equal to, so the greatest value of x to the power of 4 is going to be at half. Okay, on this range, 0 to less than or equal to x to less than or equal to a half. So therefore, x to the power of 4 over 24 is going to be less than or equal to a half to the power of 4 over 24, which is 1 over 16 times 24, which is 240, 120, 24. Hopefully I'm doing my arithmetic correctly here. So it's 240, 360, 384, right? 1 over 384. Hopefully I've done that correctly. If not, then it doesn't really make any difference. But which is, of course, less than or equal to 1 over 320. Therefore, f of x, f is an excellent approximation of g. Okay. Hopefully that's made sense. Right, so the next part. Let's scroll down, give myself a bit more space. Part 4. Show that for x greater than or equal to 0, h of x minus f of x is equal to g of x minus f of x plus the integral from 0 to x of h of t minus f of t dt. Okay, so start with h of x minus f of x, I guess. This is equal to oh yeah, okay. h of x minus g of x plus g of x minus f of x. Okay. So this is a very common thing to do in mathematics. I'm effectively adding either adding something and then subtracting it straight back off, or subtracting something and then adding exactly the same quantity back on. So what I've done here is I've subtracted g of x and then added g of x straight back on, effectively adding 0. So I'm not changing the numerical value of the expression for all intents and purposes. Okay, very common thing to do, and it's worth bearing in mind. It's worth bearing that in mind. I find this comes in particularly useful in some contexts. For example, if you've got something like x plus 3 over x plus 5, for example, rather than going through the whole rigmarole of algebraic division, you can write the numerator and denominator here as x plus 3 plus 2 minus 2. I know I'm going a little bit off here, but it's my video. I'll do what I want. Over x plus 5. So x plus 3 plus 2 is x plus 5. So you get x plus 5 over x plus 5 minus 2 over x plus 5. But x plus 5 over x plus 5 is just 1. Now, I've written out here all of the steps involved, but basically you can do this in your head and go straight from x plus 3 over x plus 5 to 1 minus 2 over x plus 5. It does come in useful from time to time, and it saves a lot of time, because I hate doing algebraic division. It's just such a pain. Anything that I can do to avoid it, I'll do. Within reason, of course. Okay, so h of x, I just need to remind myself what h of x was. It was 1 plus the integral from 0 to x of h of t dt. G of x, so we're subtracting g of x, so it's going to be minus 1 minus the integral from 0 to x of f of t dt plus g of x minus f of x. So the ones will cancel, bye bye. And then we're going to use the properties of integrals. Namely, if we've got the integral from a to b of f of x, maybe I shouldn't use f actually. I'll use uppercase F just to distinguish it. So f of x dx plus or minus the integral from a to b of g of x dx. Then this is equal to the integral from a to b of f of x plus or minus g of x dx. So I can combine these two separate integrals into a single integral, provided that the limits, if there are limits, the limits match up. Okay, so notice that here I've got the limit a, and then I've got b, b, b. Okay, wouldn't work if the limits didn't match up. Okay, so that's one of the properties of integration that hopefully you've picked up on. Sometimes it doesn't really get mentioned too much at A level, even though you kind of use it. You do use it quite often, to be honest with you. When you're integrating a sum of functions, what do? You integrate term by term, right? And it's effectively this property of integrals in a kind of disguised form. Attention's just not drawn to it. So what we've got here is the integral from 0 to x of h of t minus the integral from 0 to x of f of t. I can combine into a single integral 0 to x of h of t minus f of t dt plus g of x minus f of x. So other than the specific order in which I've written everything, I've shown what I needed to show. Now, in the exam, what I would do is actually just write it out. Just, again, do this because it only takes a couple of seconds. Just actually write things in the the exact order, and then there's no comeback. Okay, if you can rest assured then that you're definitely not going to lose any marks for just writing it slightly in the wrong order or something like that. Okay, why risk it? So we've shown what we needed to show. So far so good with this problem. It's not really presenting too many difficulties. Part 5 again is not too difficult, as we'll see. So you're given that h of x minus f of x has a maximum value on the interval 0 is less than or equal to x is less than or equal to a half at x equals x naught. We don't need to know what x naught is. We won't be able to find out what x naught is. Remember, we're not allowed to use any properties of the exponential function other than the one that we've been given. Okay, so do not attempt to try to find the value of x naught. You don't need to know it. It's irrelevant. All you need to know is that there is a maximum value. You might be able to find it out. If you are able to use other properties of exponentials and things like that, you might be able to figure it out. But it's just irrelevant to what we need. Explain why the integral from 0 to x of h of t minus f of t dt is less than or equal to half times h of x naught minus f of x naught. Okay, so now I would expect when it says a maximum value, I'm going to take that as positive. I'm going to understand that as meaning a positive. And maybe there's a way that I can well, it has to be at least 0 anyway. It has to be at least 0. The maximum of h of x minus f of x. So this is just to give a more definite reason why I think that this maximum is going to be positive, or at least equal to 0, because h of 0 is equal to 1 plus the integral from 0 to 0 of h of t dt. Well, if the two limits of an integral are equal, that integral is equal to 0. So in other words, h of 0 is equal to 1. F of 0 is equal to 1 plus 0 plus 0 squared over 2. So 1 plus 0 plus 0 plus 0, which equals 1. So that means that h of 0 minus f of 0 is going to be equal to 0. Right? So our maximum is going to be at least 0. It can't be negative. Because even if when we move away from 0 and go into to positive values of x, even if the value of h of x minus f of x becomes negative, we've still got a maximum. Then we've still got 0 as a possible value for that difference. So I would understand then that h of x minus f of x is going to be greater than or equal to 0. Okay. Right. So why do we care? So the integral from 0 to x of h of t minus f of t dt is going to be less than or equal to. So if we think about this as an area, as kind of calculating an area, and this is the way that I would really recommend that you think about this. So if you think about what the function, okay, I'll just use a generic function. So we've got f, which might look something like this. So this is f of x, uppercase f of x. Okay, between 0 and a. And if we form now a rectangle, we find the maximum value, and we draw a line that's tangent effectively to the graph of f of x at that maximum value, and we draw a rectangle. Okay, what's the area of this rectangle going to be? It's going to be the max. Screen keeps blinking. So the area of the rectangle is going to be the max of f of x over the range 0 to a times the length of that interval 0a. They're the lengths of the sides of the rectangle, right? So this is max of f of x, and then this length here is a. Hopefully that's... I'll just scroll up a little bit. I'm not sure if you'll be able to see that on the screen. Okay, so what we have is that the integral of f of x between 0 and a is certainly going to be less than that area. Again, we're interpreting as an area here. So the integral of f of x from 0 to a dx is going to be less than or equal to the area of this rectangle. That's the idea that we're going to be using here. So this integral from 0 to x of h of t minus f of t dt is going to be less than or equal to the max of h of t minus f of t times by x, the length of the interval. Okay, which the max of h of t minus f of t is equal to h of t naught minus f of t naught, because that's where the maximum occurs. Now x is less than or equal to a half. So h of t naught minus f of t naught times x is going to be in turn less than or equal to h of t naught minus f of t naught times a half, which is exactly what we needed. Right? So we're thinking about things in terms of areas. We're interpreting this integral as an area. Okay, and this is a perfectly legitimate thing to do. Right? I would definitely recommend that you think about things in that way. Okay, so moving on, we come on to the last part, and this is where things get a little bit trickier. Although there's a very obvious thing to do, and when I say obvious, I mean it's obvious once you've seen it. Okay, and it did take me a few attempts to get it right, and this is how it is, as I've said, with problem solving. So before I before I spill the beans and tell you exactly what to do or what you can do, what I usually do in these videos is I really present some of the ideas that didn't work, because even though an idea doesn't work here, it might actually be something that you can use elsewhere. Might not be, okay? But this is when you're solving problems, all of those aborted attempts at solving problems, these all contribute to your understanding. Don't think that your learning only occurs when you complete a problem. Your learning is ongoing as you're attempting to solve problems, not just when you solve the problem. So there will be some problems that you will attempt to solve and you will fail. And it's not necessarily a nice feeling, but do not be under the impression that you haven't learned anything from that. If you've had several decent attempts at the problem, you've thought about it from several different perspectives, you've tried different ideas out, you've learned a lot. You've potentially learned a lot more from doing that than if you just happened to find the right solution first time. Okay, most of your learning will occur through your aborted attempts at solving problems. oddly enough. Okay, so don't underestimate how important that actually is. So, okay, my first attempt at this. What is the problem actually? So you're also given that f of x is less than or equal to h of x. For all 0 less than or equal to x is less than or equal to a half. Show that f is a good approximation to h when 0 is less than or equal to x is less than or equal to a half. Okay, so that first thing that we're told, that f of x is less than or equal to h of x, that is the key bit of information, in my opinion. Now, to actually realise how important that bit of information is can and sometimes will take some considerable time, because you have to understand that this problem has been written from the perspective of somebody who knows what's going to happen, how things slot into place. So the person that wrote this problem knows how that bit of information is relevant. They know why they've included it, and it's not a random bit of information. It is something that is very pertinent to the solution to this problem. But that's what you've got to figure out, potentially. Okay. Now, it does happen that sometimes you are given problems where there's a bit of redundant information. And it might only be redundant when you try to solve the problem in a particular way, because it might be that you generally expected to solve the problem in this way, where you do need that bit of information, but maybe you've had a bit more insight, maybe you've been a bit more clever, and you found a much more subtle way which doesn't require that bit of information, which can happen from time to time. But generally speaking, if you're not using a bit of information and you're struggling to solve a problem, that's your reason, okay? Because you've not used that bit of information. So you've really got to dig deep sometimes and figure out what's what. So my initial attempt at this was to... so we want to show that f is a good approximation to h. So I need to consider the modulus of f of x minus h of x. And this is on the interval 0 is less than or equal to x is less than or equal to a half. Now, if you look back at part 4, we've already figured out that h of x minus f of x is equal to g of x minus f of x plus this integral from 0 to x of h of t minus f of t dt. So in other words, this is equal to the modulus. This was something that I tried that didn't work, by the way. But again, I'm showing you, because I might have done something that, even though it's inappropriate here, or doesn't work here, might be something that you can use elsewhere in other problems. So this is equal to the modulus of g of x minus f of x plus the integral from 0 to x of h of t minus f of t dt. So this is from part 4, just so you know. Now, there's something called the triangle inequality. Okay, so maybe some of you have heard of the triangle inequality, which says that the modulus of x plus y is less than or equal to the modulus of x plus the modulus of y. Okay, if you haven't come across the triangle inequality, that's it. It would be a good idea for you to maybe have a go at trying to prove that. It's not too difficult. Again, if you look at things in the right way. So this is less than or equal to, using the triangle inequality by considering this g of x minus f of x as x, and then this integral as y, then I get this is less than or equal to the g of x minus f of x modulus plus 0 to x h of t minus f of t dt. Now we've already shown that f and g, f is an excellent approximation to g, and what was it, less than or equal to 1 over 384 or something like that. I can't remember. Let's just write it as that. Plus, and we've also shown that the integral from 0 to x of h of t minus f of t dt is less than or equal to a half, and it's going to be the modulus of h of x naught minus f of x naught, which I can actually just write as half, get rid of the modulus, and I get h of x naught minus f of x naught. And also on the left hand side of the inequality, I can just write the modulus of f of x minus h of x, I can just write as h of x minus f of x. Okay, so this is what I got up to, and I thought I was onto a winner with this, because I was using the result from parts 3, 4 and 5 here, but this didn't go anywhere. Oh, I've missed some brackets off there. This didn't go anywhere. Okay, I tried all sorts of things out, and arguably there's a fine line that you've got to walk sometimes. Sometimes you do have to fixate on an idea because you have to give it a decent try. But also, I'm going to seem to contradict myself and say you can't get too fixated on an idea, because it might just be becoming blatantly obvious that it's not working, and you've got to be prepared to move on. Okay, there's no fine line. There's no definite cutoff line. There's a lot of grey area there. Where do you draw the line between giving something enough time and abandoning it and moving on? Because it can be that you make the wrong call. There's no guarantees. But so you've got to decide for yourself, especially in an exam, how much time are you going to give for something to work. Now, you do have to give things enough time, and it can be awfully frustrating when you think that you've got something that's going to work and it just, you maybe spend 10, 15 minutes on it and it just becomes obvious that it's not going to work. At that point, I mean, you've got to make your own decision, but really think very carefully about whether you want to carry on with it. Because it could work, but it might take you another hour of work to figure out exactly how it's going to work. It might be better to move on to something else. So I tried all sorts of things here. I was thinking, because we know that, for example, h of x naught minus f of x naught is going to be greater than or equal to h of x minus f of x, because remember that h of x naught minus f of x naught is the maximum value of h of x minus f of x. Then we know that this holds. So I tried to kind of mess around with this a little bit, but nothing seemed to work. So I'm not going to write out all of the stuff that I tried out, but just nothing, it didn't produce anything that was worth pursuing. Okay, but the main thing is that I tried something out. So probably spent about 10 or 15 minutes playing around with this, and it didn't work. And then eventually I realized how obvious this actually is. So we do need to use the result from part 4. We do need to use that. But we also need to use the bit of information that we're given right at the start of part 6, which is that h of x is greater than or equal to f of x. Because that means that h of x minus f of x is greater than or equal to 0. So, going back to the result from part 4, h of x minus f of x is equal to g of x minus f of x plus this integral. Then I get 0 is less than or equal to g of x minus f of x plus the integral from 0 to x of h of t minus f of t dt. And this is for 0 less than or equal to x is less than or equal to a half, remember. Okay, good. So then I can rearrange this, and I get the integral, or minus the integral, from 0 to x of h of t minus f of t dt is less than or equal to g of x minus f of x. This is when I knew that I was onto a winner. Definitely. Because now I can modulus each side. So, okay, I'll take the modulus of this, the modulus of this. And what does that give me? It gives me the integral from 0 to x of h of t minus f of t dt. Aha! Modulus of g of x minus f of x, that's less than or equal to 1 over 384, since by, and do cite this in your solution, since by 3, f is an excellent, or maybe I could say, it has been shown. It has been shown that modulus of f of x minus g of x, or g of x minus f of x, whatever, is less than or equal to 1 over 384. For 0, less than or equal to x is less than or equal to a half. Make it clear where you're drawing your conclusions from. So now, this integral on the left-hand side, we know is what have I done here? Less than or equal to actually, I think I should have done this sooner, actually. Yeah, okay, right. I'm going to backtrack. Sorry about this. I'm going to backtrack a little bit. I'm just going to change this bit here. I should have done this sooner. So I'm going to get rid of this because this integral, remember, from part 5 is less than or equal to a half, what is it, plus a half h of x naught minus f of x naught. So, okay, correcting this then, we get rid of this integral here. And we get over here minus a half h of x naught minus f of x naught, which is, get rid of that, half modulus of h of x naught minus f of x naught. There we go, that's better. So that means then that h of x naught minus f of x naught is less than or equal to 2 over 384. Oh my goodness. So that's going to be 1 over 192. But modulus of h of x minus f of x is less than or equal to the modulus of h of x naught minus f of x naught. Because remember, h of x naught minus f of x naught is the maximum. So the modulus of h of x minus f of x, And also h of x minus f of x is going to be positive, is going to be greater than or equal to 0 as well. Okay, we need to take that into consideration. Is less than or equal to 1 over 192, since we know that this is less than or equal to 192, 1 over 192. So therefore, 0 less than or equal to x is less than or equal to a half. So f is a good approximation of h. Okay, I'll scroll down a little bit so you can see that. Okay, so yeah, I messed up a little bit at the end there, but hopefully you understand what the argument is. There is a reason why it was important for me to why I had to backtrack and replace that integral with this expression at this particular stage. I'll leave you to have a think about why it was necessary for me to do that, rather than leave it to a later stage, like I initially did. I actually didn't do that. I did. That was a mistake that I just made now in this video. Anyway, beside the point. Hopefully you found that something useful in that. Again, the whole point of these videos is not just to provide just a simple worked solution to the problem. It's actually to provide some sort of commentary to my actual solution, and for you to actually see how things work, how a solution can develop. So I'm not going to edit that out. The mistake that I made, I'm going to leave that in. I'm not going to edit that out. That's for you to see, so you can see how the problem solving process works a bit more accurately. If there is anything that you didn't understand, please let me know in the comments section. If necessary, I can always make the video again if it's not terribly clear. But if you do get some benefit from these videos and you do want me to keep making these videos, please hit the subscribe button and hit the like button and show your support for this video, for this channel. I don't make any money from making these videos, as you can probably tell. But I can only really justify making them if I do actually have the support for making them. So if you do appreciate these videos, you would like me to continue making them and giving you this information for free, please let me know. Please show your support. Be much appreciated. And if there is anybody else that you know that also might benefit from these videos, let them know as well. So that brings us to the end of this problem. Any questions you have, let me know. But thank you for watching, and I'll see you in the next video.